State in order the sequence of transformations that have occurred to y equals the square root of x to give the equation shown below. The first thing we need to do when we're doing this is to reintroduce the dashes onto the variables x and y as shown. The next thing we do is we rearrange this equation to make it resemble the basic equation y equals the square root of x as much as possible. So to do this, we're going to start by subtracting 3 from both sides of the equation, and this will give us y dash minus 3 is equal to the square root of 5 minus 2x dash. We now have a series of terms involving y equaling the square root of a series of terms involving x, which means it is resembling our original basic equation, y equals the square root of x. So the next thing we do is we equate this part to be y and the bit inside the square root sign to be x. So this gives us two equations. One is that y is equal to y dash minus 3, and the other equation is that x is equal to 5 subtract 2x dash. Next, we need to solve for the dash terms in each of these equations. So for the equation involving y, we're going to add 3 to both sides of this equation, and that gives us y dash is equal to y plus 3. For the other equation, we're going to start by subtracting 5 from both sides of the equation. So this gives us x subtract 5 is equal to negative 2x dash. And then to get x dash by itself, we're going to divide both sides of the equation by negative 2. And this gives us x dash is equal to negative 1/2 x plus 5 over 2 when you do the division by negative 2. So we can now use these two equations to put it back into mapping notation, which can assist us to determine the transformations that have occurred. So we can say that x comma y has been mapped to, and now the x has become, from this equation, minus 1/2 x plus 5 divided by 2, and the y value has become y plus 3. From the previous slide, we found this mapping notation, which we will now use to interpret the transformations that have occurred to y equals the square root of x to give this equation y1. It's also important to note that we can determine the transformations directly from the rule, but to do that we need it in a certain form. And that form needs to have the negative 2 factorized out from the expression under the square root sign. So here we have that equation, and we'll see how this links with the mapping notation to give us the transformations that have occurred. So the first transformation is that it has been reflected over the y-axis. So we know about that transformation because of the negative sign that's being multiplied to the x term in the mapping notation, which reflects all of the x coordinates across the y-axis. And from our rule, we can see the negative that's out the front of the x value in that rule. Next, we have a dilation by a factor of 1/2 from the y-axis, and once again this comes from the half that is being multiplied by the x in the mapping notation, or from the rule, this dilation of a factor of 1/2 comes from the 2 that's multiplied by the x. So it's a little bit trickier to discover what dilation factors have occurred from the rule than it is from the mapping notation. Next, we consider the translations that have occurred. So we have a translation of 5 divided by 2 units in the positive x direction, and that comes from the plus 5 divided by 2 in the mapping notation here, or in our rule, the negative 5 divided by 2 inside the brackets there. It is also translated 3 units in the positive y direction, which comes from the y plus 3 in the mapping notation, and the plus 3 here is responsible for that translation of 3 units in the positive y direction.